Hello there. On a previous video on this channel, I explored the coupled two spring mass system, in which we had two blocks of equal mass m connected by springs of spring constant k, as I'm showing here. And in that video, we derived this very carefully. We derived the equations of motion for these two blocks, and they looked exactly as I'm showing here. If you feel comfortable with, the process of how we derived that, remember what we did. We imagined, let's say I have block 1 here. I'm looking at block 1, right? Then what we did is first we imagined holding block 2 fixed, and then giving block 1 some positive displacement to the right. And what we saw, the first spring would stretch out and pull block 1 back, and then the second spring would compress and push block 1 back, so that gave us this -2 ultimately. And then after that, what we did is we held block 1 fixed, gave block 2 a displacement, and then we saw this middle spring stretch out, which would then pull block 1 to the right, and so positive displacement, positive force, and so we gave this +1 here, right? So that was our process, and then we did the exact same thing for block 2 to get that row there effectively. But go ahead and make sure that you're feeling really good about these equations of motion right here, because that's going to be the starting point for this video. Because what I want to do is I now want to imagine taking this 2-mass system, and what we're going to do is we're going to put more and more blocks in here, and eventually we're going to turn this into a continuum of springs and masses, right? And what we're going to show is that, as we take this limit, as these number of springs and blocks goes to infinity, we're going to see a wave equation come out, okay? And that's what I want to explore in this video. Okay, so let's go ahead and upgrade to the 3-mass system here. Okay, now I've put in one more block. And I'm just writing down the results of what that matrix would end up looking like. These are the equations of motion for the 3-spring mass system, right? And go ahead and make sure that we're feeling comfortable about, how this came about. We'd have to do the exact same process as in the 2-block system of going, all right, I'm interested in equation of motion for block 1. I hold block 2 and block 3 fixed, displace block 1. That gives me this -2. Next, I hold block 1 and block 3 fixed, displace block 2. That's going to give me this 1. And then of course, holding these other 2 fixed, stretching out block 3 isn't going to stretch out the springs at all for block 1, and that gives us this 0 here. But again, I'm not going to go through the full process in these matrices because that would end up, taking a long time. What I'm more interested in is looking at the results of these, equations of motions and picking up the patterns on them. Okay, that's the focus here. Okay, so for example, look at this terminating behavior. Look at this end behavior on the walls, right? These are the equations of motion for block 1 and block 3. Block 1 has this wall to the left of it. Block 3 has a wall to the right of it. And what we're going to see, right, is block 1 is going to have this -2, 1, followed by zeros behavior, right, because it's on the left wall. And block 3, being on the right wall, is going to have a bunch of zeros followed by 1 and -2, right? And then what we're going to have is kind of, the blocks in the middle, right? So, if this is like a sandwich, these are the pieces of bread on the sandwich, and then this is the meat here in the middle of the sandwich, right? Which is what we're really interested in, okay? The middle is always going to have this 1, -2, 1 behavior here, right? It's always going to have that kind of symmetric 1, -2, 1 behavior, okay? And that's really, really important. All right, let's go ahead and level up again. Now we have 4 masses, okay? And again, we're seeing the exact same thing, right? Because now we're kind of ready to see the pattern. minus, terminating behavior on the top and bottom. -2, 1, followed by zeros. Zeros followed by 1, -2. Great. And then in kind of the meat of our sandwich here, what we're seeing is we have this 1, -2, 1, right? And these are going down diagonals, right? We're basically getting this diagonal behavior here where, as we trace down these diagonals, we're able to see these 1, -2, and 1s, just propagating through the matrix. All right, so are we feeling awesome about the patterns here, right? Could we, come up with what would the equations of motion for a 5-mass system look like without even hardly thinking, just by following the patterns? All right, if so, now I'm just going to go straight to, let's imagine a system of n masses, right? In which case we're going to get, more or less the exact same thing, that we've been seeing up until this point. First off, our matrix here is going to be n by n. That's going to be the size of the matrix, right? And we're going to get, this terminating behavior. Oh yeah, real quick for the notation, right? These zeros here, these giant zeros, imply that every slot, in this top right and this bottom left kind of corners here of this matrix, they're all going to be filled with zeros. That's what that notation means, okay? But the point is, we see the exact same behavior, -2, 1, followed by a bunch of zeros, down this row, and, zeros followed by 1, -2, and then our diagonal kind of behavior, 1, -2, 1, right? And now, for big N, obviously, the tops and the bottom rows are, not the main focus of interest. It's all this middle stuff in the middle here, right? Because if we have 500 masses, right, the exact behavior of these kind of end masses is kind of trivial compared to, the 500, in the middle, right? All right, so one question to ask, and it's a really good question actually, is, well, are we just done with the problem? Because right now we basically have this cookbook here for you give me some number of masses in series with each other connected by springs. I have every equation of motion necessary to describe this system. Am I done? Right? And the answer is kind of yes, but not really, right? Because the reality is, if we want to imagine, actual systems of particles like an elastic band or something like that, this n is going to approach Avogadro's number of molecules, right? We're going to have some massive number of molecules in this continuum here, and suggesting that we have this a matrix of an Avogadro's number of size, 10 to the 23rd on that scale, that would just be ridiculously huge, right? So, fortunately, we have this tool calculus, right, that lets us, approximate massive numbers as infinity, right, and come up with, more or less approximating things instead of discrete numbers of particles as continuums of molecules, taking a limit as things go to infinity. All right, so before we do that, before we start using calculus, let's go ahead and pluck out kind of this pattern and let's make this official. Let's use some indexes and stuff in order to make this clear. So let's go ahead and associate so this -2 is going to be multiplying, somewhere in here, so somewhere down, this vector of displacements here. This is going to be multiplying some x sub j, okay? So to the left of this 1 is going to be multiplying some x times j minus 1. And this, this 1 to the right here is going to be multiplying some x sub j plus 1. Do you see what I'm saying? So I'm defining the term that that each -2 is going to multiply. I'm going to define that as some x sub j. And then, the 1's going to multiply the term before that, and this 1's going to multiply the term after that. So I'm going to call that x sub j minus 1 and x sub j plus 1. Okay? So really what I'm going to have on this left-hand side, I'm just going to pull this out. I'm going to have k over m times x sub j minus 1 minus 2 times x sub j plus x sub j plus 1, and this is going to be equal to, right, what's it going to be equal to? This is going to be equal to x sub j double dot. This is going to be the acceleration of the jth mass that we're interested in, right? Again, each row goes along with, this would go with x sub j here, double dot, the acceleration of the jth mass, okay? So that's all that I'm doing. Now I'm just pulling out the pattern and making it official. Like, okay, great, we have this pattern. And again, we're kind of ignoring this terminating behavior here because that's not the bulk of our pattern, especially when we're, going to be talking about things on the scales of like 10 to the 23rd molecules. And don't really care about this. I care about this continuum pattern here. All right, so with this, we are ready. We're ready for the kind of the final level here. Now I have some infinite continuum of masses. Okay, I have this like elastic band here. Okay, and the first thing that I need to do is, instead of kind of using these index notations, we're going to see how this all works out in a second. What I need is I just need to measure a position along this band. Okay, and I'm going to go out, some amount, and I'm going to measure this position along the band, and I'm going to call this position chi. Okay, not x, right? Because we're already using x. Go ahead and remind me for a second, what does x represent? X represents, right, like when we were back over, from the very beginning, x1 here, that represented the displacement x1, right? So block 1 has some displacement from its equilibrium position x1. So that's what the x's are saying. And in this continuum limit, basically what we could think is we measure some position chi, right, some location on this band, and then x is more or less measuring some disturbance away from this chi at that location on the band. Okay, so that's kind of how we can think of this. But the point is, let's go ahead and start, bringing some calculus into this. Is, so I've got some particle located at chi. The next particle is going to be located at some chi plus delta chi. Okay, and what's going to be really important is, let's also go ahead and recognize that the particle to the left of chi is going to be at some chi minus delta chi. Okay, do we see that very, very clearly? I wonder how that corresponds to all of our stuff up here. Well, x sub j minus 1, this is going to be some x at, per some location, x minus delta chi. X sub j goes to x at some location chi. And x sub j plus 1 goes to x at some chi plus delta chi, right? We're replacing these discrete indexes with, this is some disturbance at some location chi, plus or minus some amount. Okay? Are we super clear on, how this is coming about here? Okay? We're trying to take this transition. We're taking this transition from these discretized x sub j's into something where we can take a limit, right? That's kind of our objective here. Okay, and really, okay, just in case this is, some element of concern, right? Technically, each of these x's are also functions of t, right? At the end of the day, these disturbances, these, displacements are really, they're like oscillating with time, right? So they always have this time dependence here. That's why also on the right-hand side here, we can take, time derivatives, okay? I'm kind of omitting that to make life easier, but if we wanted to be mathematically formal about all of this, we really should be including the fact that these are multivariable functions throughout this thing, right? But I just want to focus on kind of the key ideas here. Okay, so now I'm going to go ahead and plug in, right? I'm going to plug each of these guys in, and we're just going to go ahead and create our, our equation of motion more or less. So we have k over m times x at some chi minus delta chi minus 2x sub, at some chi plus x at chi plus delta chi. Ooh, let me write that nicer. Plus delta chi. And this is going to be equal to x at some chi double dot. All right, awesome. All right, and now let's go ahead and take a look at something. This is just a picture, off of Wikipedia. I just snipped this real quick. This is the limit definition of the second derivative. They're looking pretty close, right? Not completely there, but replace h with this delta chi here, and we're pretty much looking at the same thing. We're really, really close. And first off, does taking this limit as delta chi goes to 0, does that make sense? Yes, absolutely. As we take the limit as the number of springs goes to infinity, right? As we take that limit, then the distances between each of those, each of our masses is going to get smaller and smaller. And so, as a result of that, delta chi is going to go to 0. So yes, that's absolutely the limit that we want to be taking here. Okay, so that's our objective. Okay, is there anything else in here that we can rewrite? Because all that we need now, we just need this some delta chi squared on the bottom of this thing, and then we can take a limit. All right, so let's go ahead and look at this k over m, see if we can extract some delta chi squared from this. And in fact, yeah, now that we think about it, we haven't looked at this at all in kind of this process of, replacing things in terms of delta chi yet. So in fact, if this bar or this elastic band is some material, right, it's going to have, portions of delta m associated with it, right? It's going to have these portions delta m associated with each section. And the reality of, this is that this is going to be some 3D band. So let me look at a cross section here. It's going to look something like this, right? This is a little cross section of this delta m here. And it's going to have some constant area A, in this little cross section. And, it's going to have some length of delta chi. You get what I'm saying, right? And so we have this wonderful tool. It's called mass density, right? We know that my mass density rho is defined as some change in mass per some change in volume, which is going to be equal to, right, delta m over delta chi times A. And so we can substitute in for delta m, this is going to be equal to rho times A times delta chi. So that's the first thing. So now I can go back to this m here and say, and we're going to replace this with rho times A times delta chi. Excellent. Okay? Because now we're bringing this delta chi language into the picture here. Okay, what about with this spring constant k? Well, we can do something very, very similar using Young's modulus. Okay, in the stiffness, okay, just as a reminder, the stiffness, and I'm going to call this capital K of any given material, is defined as some constant, Young's modulus, times A, the cross-sectional area of that object divided by, the length of that thing that we're interested in, right? And so again, just to bring back, I'm just going to draw that same kind of cross-sectional picture here that I used for my delta m's. Again, we have some cross-sectional area A. Now, instead of thinking about the mass nature of these kind of pieces, let's think about the springy nature of these pieces, right? Right. Before, these were our springs of, some little k. That's what we're trying to replace here, right? And what was the length of each of these pieces? Well, we said, in our picture, each of these had some length delta chi here. So in other words, right, the spring constant k, little k, for each of these little springs is going to be equal to EA over delta chi. Awesome. So again, we go in here and we say, we're not interested in, measuring k for each spring. That's kind of losing meaning now as we're entering this continuum language. We're going to replace this with, this is now EA over delta chi. Great. Areas cancel out. Awesome. What are we left with? Sweet, we have delta chi. That's going to give us a delta chi squared and an E over rho. So let's go ahead and write this out one last time. I'm going to have E over rho times, put it all together now. I have x chi minus delta chi minus 2x chi plus x sub chi plus delta chi all over delta chi squared. And this is equal to x double dot of chi. All right, and now what do we want to do at the very end here? We want to take the limit as delta chi goes to 0. And we're going to be left with one very beautiful equation. E over rho times the second derivative of x with respect to chi. Look, on the right hand side, we have this derivative with respect to time, and now we're getting this derivative with respect to chi. So we need to use a partial derivative language here because we have a multivariable function. So we have e over rho d squared x with respect to chi squared. And this is equal to d squared x dt squared. And this is the form here. This is the form of a wave equation. Okay? The disturbances in this material, right, they take the form of waves, right? Now, I haven't gone through and solved this equation analytically. Maybe I'll do, solutions to the wave equation in some video down the line. But I think by the name, you can assume that, people have solved this in the past, and, we find that the solution to this are waves, effectively, right? And, this is so cool, right? That we started with these discretized systems, right? Blocks and springs, so really like simple, easy things to think about. And then we just added more blocks. And then we thought of things as a continuum limit, and then when we did that, we ended up spitting out this beautiful wave equation here that tells us everything that we kind of need to know, about these complicated, infinitely many kind of spring-like systems. I mean, that's awesome. So, again, we kind of solved this problem that I brought up in the middle of the video. No, we don't need, these 10 to the 23rd sized matrices to deal with, a mole of springs and molecules kind of in series with each other. That would be so much work. Now we're just down to one beautiful kind of equation here that we can solve because we took this infinite limit. We made things a continuum. And that is just so powerful. Alrighty, so I'll go ahead and wrap this video up here. If you enjoyed the video, found it helpful, let me know in the comments, and consider subscribing to the channel. I love to hear about people getting on board. But other than that, thank you so much for watching.